So in the last session we started with the analysis of nonlinear systems using describing function method, and we proved the existence of a limit cycle using the describing function. Now in this session we'll be looking at the stability of limit cycle or a nonlinear system in general, and using the describing function method. So describing function, as I have earlier also said, it's an extension of Nyquist criterion. So as far as the Nyquist criterion goes, just yeah, we have already covered the Nyquist criterion for linear control systems. For a linear system described by its open loop transfer function g of s, and with a unity feedback, for the system to be closed loop, we actually analyze the characteristic equation of the system. Right? If we have a system whose open loop transfer function is g of s, it is the characteristic equation 1 plus gs equal to 0 that actually helps us in understanding whether the system is stable or not. So what we do is, from here we can say that gj omega is equal to minus 1 becomes the critical point fixed for linear systems, along which we actually determine whether the system is stable or not. So for a stable open loop system, we actually see whether gj omega when enclosed minus 1 will cross through minus 1 point, or it will be actually the minus 1 point will be not enclosed by the gj omega line. Right? So we actually have three conditions wherein gj omega locus will not encircle the point minus 1 plus j omega. So this is our minus 1 plus j0 point. So you can have a system which will not enclose, this is the locus of gj omega, it does not encircle the point minus 1 plus j0, and hence we can say for the open loop, if the open loop system g of s is stable, the corresponding closed loop system shall be stable as well. Fine. So this is what we interpret from this. Second, if the gg omega locus passes through the minus 1 point, we can say that the system will exhibit oscillatory behavior. So this can be the second case. The first case, where the gg omega locus does not encircle the point minus 1, and so therefore if the open loop system is stable, the closed loop system will also be stable. If it if the open loop system gg omega is stable and the gg omega locus passes through minus 1 point, we say that the system response is oscillatory. It's a marginally stable system. We are talking about linear systems. And if gg omega encircles the minus 1 point, the closed loop system in that case is said to be unstable. So this can be the third type of response. So if gg omega locus encircles the minus 1 plus j0 point, then the closed loop system is said to be unstable. So this is only valid for the open loop, for a stable open loop system. For an unstable open loop system, the Nyquist criterion actually changes, and we need to keep in mind it may or may not be stable for even if it does not encircle minus 1 point, it may or may not be stable. We have to analyze that for a unstable open loop system. This is valid, the Nyquist criterion is only valid, and these 3 points are only valid for a stable open loop system G of S. Now this same criterion can be extended to analyze the stability of a nonlinear system as well. So analyzing the stability of a nonlinear system, say for example again, we have a nonlinear element, we'll be having a linear element, so this is our nonlinear element, this is our linear element in this case for r equal to 0. Now the characteristic equation of this system becomes 1 plus nx g j omega equal to 0. So therefore n of x into g j omega is equal to -1, or we can say g j omega is equal to -1 by n of x, where n of x is the differential, the describing function of the nonlinear element. So let this be equation number 1 and this be equation number 2. So it is the equation number 2 that will actually determine the critical point and help us in understanding the stability for nonlinear systems, where g j omega is equal to -1 by nx. So we know from the linear systems there are 3 cases where the g j omega locus encircles the -1 point, g j omega locus passes through the -1 point, and g j omega locus does not encircle the -1 point, and these respectively mean an unstable, a marginally stable, and a stable system for a stable open loop system. Fine. Now this equation number 2 that we have seen, g j omega equal to -1 by nx. To find out the solution of this equation, we'll be basically plotting the g j omega locus in the complex plane, the complex S plane, and along with this we'll also plot the locus of the curve -1 by nx, and by actually varying omega and x respectively. Fine. So what we'll be doing, we'll be plotting g j omega by varying omega. So this is a simple polar plot, and we'll be also finding out the locus of -1 by nx by varying x. So you can have a graph like this. So this can be g j omega, this can be -1 by nx. Fine. So this can be the locus of g j omega, this can be the locus of -1 by nx. Now from this actually 3 different cases will arise. So what are those 3 cases now? G j omega plot is enclosed by minus 1 by nx curve. GG omega plot is not enclosed by minus 1 by nx curve, and GG omega plot actually intersects the minus 1 by nx plot, and these three cases need to be analyzed, and from these three cases we can actually say whether, if the system is stable, if the system is unstable, or if we're talking about the limit cycles. Also from here we'll be looking at how limit cycle can be determined from this plot as well. So from these two curves now we'll be analyzing the limit cycle as well as the stability behavior of the system. So limit cycle. So how can we determine the system is exhibiting limit cycle? If the intersection of GG omega, if GG omega locus intersects the minus 1 by nx curve, the system exhibits limit cycle, and number of intersections means as many number of limit cycles. Now once we have plotted GG omega and once we have plotted the minus 1 by nx curve, now as many times they intersect, that means there are as many number of limit cycles. So for this system, this is randomly curves that I have drawn. So for the system you can say there are two limit cycles. So there can be a case where you have a case like this. This is GG omega, this is minus 1 by nx. So this means there is only one intersection, that means there is only one limit cycle. So there can be a case where GG omega and minus 1 by nx do not intersect, that means that actually the limit cycle for such a case does not exist, for such a system does not exist. Also the point of intersection, what does the point of intersection give us? So it will actually give us the value of omega and x, the frequency and the amplitude of the limit cycle is the point of intersection gives frequency and amplitude of the limit cycle as well. So whatever is the value of omega and whatever is the value of x at that time, that actually is the value of frequency and amplitude of the limit cycle of that system. Now we can analyze, we have seen that there can be as many number of limit cycles as the number of intersections. We can find out the frequency and amplitude of a limit cycle from the point of intersection, and also we can determine the stability of stability of limit cycle can be determined. So all this information is available to us from the transfer function of the linear system and the describing function of the non-linear element. The locus of those points that we have basically drawn. Now, how to determine stability? Now, what the Nyquist criterion says, if the point of intersection, if the point actually that is near the intersection and it's along the increasing value of x for the curve minus 1 by x, and it is not actually enclosed by the g omega point, then the corresponding limit cycle is said to be stable. Or we can say the stability of a limit cycle is determined by finding out whether the gj omega plot encloses the minus 1 by nx curve or it does not enclose the minus 1 by nx curve. And also will be seen for an increasing value of x towards which direction actually the minus 1 by nx curve is headed. That means value of x for which the minus 1 by for which the gg omega plot, the locus of gg omega encloses the minus 1 by nx curve that is actually the minus 1 by nx plot will lie to the right of the gj omega plot for all positive frequencies, fine, for increasing values of omega. So this means the system is unstable. Not the system, the point is unstable. So this is the case. So this is minus 1 by nx curve for increasing value of omega. This is our minus 1 by nx curve for increasing values of x, and this is our gg omega curve for increasing values of omega. So what we see at this point of intersection is that the curve minus 1 by nx lies to the right of gg omega locus, what is actually enclosed by the gg omega locus. So this point actually corresponds to a limit cycle. So we can say this limit cycle is unstable. So for increasing values of omega and x, the locus of minus 1 by nx is enclosed. So this limit cycle is unstable. We are not talking about the system now. That is what we have been studying for nonlinear systems. A particular point is unstable. Or if the values of x for which value of x this is actually unstable, value of x for which gj omega locus does not enclose the so gg omega locus will not be enclosing the minus 1 by nx curve, or that means in other words minus 1 by nx curve will lying to the left half of the gg omega locus. So that point is stable. this can be a case. This is our gg omega, this is minus 1 by nx. So you can see gj omega, this is for increasing values of omega, this is our minus 1 by nx curve. So at a point we are saying that what is happening is that the minus 1 by nx curve will be lying in the region to the left of the traversing path of actually gj omega plot for positive frequencies, for increasing frequencies of omega. So therefore this will correspond, this is for increasing values of x, this is for increasing values of omega, this is the minus 1 by nx curve, this is the gj omega curve. So this limit cycle will be therefore stable. So it's moving towards this point is moving towards the left of gg omega, the minus 1 by nx curve is moving to the left, it is stable. It is moving to the right of gg omega, it is unstable. This stability of limit cycle can also be judged by using the perturbation technique, and that will be taking up in the next session. Along with that, we'll be looking at some examples for the systems that we have already for the systems for which we have already derived the describing functions like on-off relays, saturation, etc. We'll incorporate them along with some along with some linear systems and try to find out the stability of those systems. So this is clear what a stable limit cycle means, what an unstable limit cycle means, how we can actually say a limit cycle exists. Simply the intersection of minus 1 by nx with the gg omega means the existence of a limit cycle. Now whether it is stable or not, that will depend upon for increasing values of omega if the gg omega is enclosing the minus 1 by nx curve or if it is not enclosing the minus 1 by nx curve. And respectively that means unstability and stability. And now we are talking about stability of limit cycles. With Nyquist criterion for linear systems we are talking about stability of the system, but with Nyquist criterion when extended to nonlinear systems we are talking about the stability of that particular point that actually represents the limit cycle. So we are saying whether that point, that limit cycle is stable or unstable. In general we are not talking about the system as a whole. For us, for this case, for this very case that we have actually drawn here, there are two limit cycles. So limit cycle number 1, for increasing values of omega, the system is trending towards the right, the minus 1 by nx curve is trending towards the right of the gg omega axis, the gg omega locus. So it's actually an unstable limit cycle, while as this second case that is of another limit cycle, it is not being for increasing values of omega. You will see that this point is not being enclosed by the gg, the minus 1 by nx curve is no longer being enclosed by the gg omega locus. So therefore it means that this particular limit cycle is stable. So the same system will be having number of limit cycles. Some limit cycles can be stable and some limit cycles can be unstable. So similarly you can have 3 limit cycles in a system, you can have a number of limit cycles in the system, and you have to determine the stability of each and every limit cycle for the system. So that's all for this session. We'll be continuing with the perturbation technique in the next session.